Okay, let's start with section 3.2, the product rule. This product rule is very useful whenever we're trying to differentiate or take the derivative of a function in which we see a product. You may think that because we have a sum rule where we take the derivative of a function that is adding, then it's just simply add the derivatives. That is not the case for product. So in this example, we have, if we define f of x as x and g of x as x squared, you know that if I multiply these two functions, I want to get x cubed. So if I'm trying to take the derivative of the first one, the derivative of x is 1, the derivative of x squared is 2x, and if I multiply these two derivatives, the answer is 2x. But when I'm trying to take the derivative of x cubed, this is 3x squared, which is not the same as 3x squared. So definitely I can now just multiply the derivatives of each. So, and it is stated here, the derivative of the product is not the product of derivatives. Okay. Now there's a demonstration of why this product rule works, or it's actually an explanation of why it is that we can actually take the derivative of a product. And this is very common along the book. I'm going to call u f of x in v g of x, just to make it a little shorter, to write any argument. So just so you know, u is a function of x and v is a different function, but both of them depend on x. It is just the same idea as saying y equals f of x, but I don't want to use y, I want to use two different functions, so let's just call them u or v. But those are arbitrary, but think of them as functions. So we can have this rectangle where I see the products of these partial areas, and I see the product of the entire area. So let me just translate this part. If I'm defining a function, so a small change in this function, it is just the difference of f evaluated at x plus that small change in x minus f of x. And if you remember, if you recall the formal definition of derivative, this just would be the top, this just would be the numerator of the equation that we take the limit for. And similarly, a small change in v can be found by the difference of both y coordinates, the first one being g evaluated at x plus that small change in x. So this is what we are trying to find, how much it changes, how much is the change in y, and y defined as the product of these two functions. So this is just algebraically, this change would be defined as the product of this times this, which will be the big rectangle, and then we are taking away this small one, and this is reflected right here, and that is when I have the big rectangle and I'm taking this smaller one, what I have left, which means equals to, and these three areas that we have here. And so again, the change in the area of the rectangle, which will be the reflection of the change of the product of these two functions, it can be described as the shaded area here, which could be written in two ways, as the area of the big rectangle minus the small one, or as the sum of these little three. So if we see the change on functions as a rate of change, I'm allowed to divide every term in here by the change in x. So the change in the product by the change in x equals u change in v by change in x plus v changing u respect to x plus the change in u times the change in v respect to x. And now if we are making the change in x approach 0, what we're doing is taking the actual limit. So when I'm taking the limit, this will be the definition of derivative. So what I'm finding is the derivative of the product is the same as the limit of this rate as the change in x approaches 0. Remember, x is going to change very, very little. And that will be equivalent to taking the limit of this expression right here. Now, as I'm changing x very, very small, almost like nothing, this limit right here is the one that becomes 0. So therefore, the third term gets canceled out, and the derivative of a product is simply the sum of the first function multiplied by the derivative of the second function, and the second function multiplied by the derivative of the first, as you can see on the next slide right here. And this would be the product rule. Now, written in a different way, let's just go back to f and g, and it says that if f and g are both differentiable, and this is something that we usually don't check, but just make sure that you keep this in mind, because sometimes the product you may not take the derivative of it just because one of the functions is not differentiable. So the derivative of the product of two functions is just the first function times the derivative of the second plus the second times the derivative of the first. So let's talk about example 1, and we're going to apply the rule. If this is f of x, then find f prime, which is the same thing as finding the derivative of f, or finding the directions may say differentiate f. All of them differentiate f. Okay, that's better. Okay, so let's apply the product rule. I know that this is f, but this is not the f from the product rule. I notice that f is composed out of two functions. The first one is x, and the second one is e to the x. So you may think of this as your u, and you may think of this as your v, or your f and g of x, but since we're using f, so let's just stick with u and v. It really doesn't matter, everything is the same. Okay, so let's apply the rule. F prime of x will be the first function, which is x, times the derivative of the second function respect to x, plus the second function, which is e of x, multiplied by the derivative of the first function respect to x. The derivative of e to the x, we've seen that is e to the x, so this is x e to the x, plus the derivative of x respect to x is 1, so this is just simply e to the x. And ta-da! We found f prime of x. Now, in part B of example 1, it says, find the nth derivative of f. So, I don't know if you notice, f prime of x equals x e to the x plus e to the x. When we take the derivative respect to e to the x, it kind of never goes away. So I'm getting the feeling that if we do this a few times, we're going to find some kind of pattern, so that when I take the nth derivative, then we can just replace that with n. So let's take the second derivative. This is again a product that happened to look like the original f of x. So I'm just going to write what the derivative was. So I remember that the derivative of x e to the x turned out to be x e to the x plus e to the x from the previous example, the previous part of the example. And now I'm going to add the derivative of e to the x, which is e to the x, Remember that the derivative of a sum is just the sum of the derivatives, so I don't have to do anything else. Let's take the third derivative now. Again, this is a product, and I know its derivative, x e to the x plus e to the x. And then, what is the derivative of this? Is itself. And then the derivative of this one. So, let me just summarize this, what I see. X e to the x plus 2e to the x. And this one will be x e to the x plus 3e to the x. So now let's take the derivative here. I'm taking the fourth derivative. So this is how I write it, with a 4 between parentheses. Let's take the derivative here. The derivative of the first part, I know it. X e to the x plus e to the x. The derivative of 3e to the x is 3e to the x. So this just gives me x e to the x plus 4 to the x. So when I have the nth derivative of this function, what do you think we're going to have? Apparently the first one stays the same, and then this coefficient matches with the same number as the derivative, so I'm guessing this is the n times e to the x. And that's how I find the nth derivative. Just remember, n is just any number. This is some kind of a formula, so let's say that I want, for some reason, the 20th derivative of this function. I don't have to take the derivative 20 times. I can just say this is x e to the x plus 20 e to the x, and my job will be simplified just because of that.